Hello viewers, welcome back to the YouTube channel. In today's video, I will discuss about ghost spectrum or ghost lines in grating, resolving power and resolving power of a grating, diffraction from crystalline material, Miller indices and Bragg's law of diffraction. The topics would be discussed as per the syllabus of MAKAUT BTech Physics, paper code PH 101 or 201. First year engineering students of any other university or institution may also follow this video to prepare for their semester physics paper examinations. Before starting the class, if you have not still subscribed the channel, then please subscribe the channel and like and share those videos with others. In addition to these theory lectures, if you want to join numerical problem solving classes and also theory classes for MAKAUT BTech Physics syllabus, paper code PH 101 or 201, you may join my online classes. For online classes, you may contact me through the WhatsApp number given in the screen, and also you can contact me through the Facebook and Instagram page. Everything has been given in the background of my screen. So without wasting time, let us start the class. So at first, I will discuss about what are ghost light or ghost spectrum in grating. Now ghost lines or ghost ray lights means they are fake or unauthentic spectral lines that arises from the periodic errors of the grooving of গ্রেটিং অর রুলিং অফ গ্রেটিং। গ্রেটিংয়ের যে রুলিং অর গ্রুভিংটা করা হয়, সেই গ্রেটিংয়ের গ্রুভিং অথবা রুলিংসের যদি কোনো এরর থেকে থাকে, ফর দ্যাট এরর দ্যাট আনওয়ান্টেড লাইট অর আনঅথেন্টিক স্পেকট্রাল লাইন্স দ্যাট আর ক্রিয়েটেড ডিউ টু দ্যাট এরর্স অফ রুলিংস in grating, those unwanted lines are called ghost spectrum or ghost lines. Ghost spectrum or ghost lights in grating are defined as spurious, that means fake or unauthentic spectral lines that arises from the periodic errors in grooving or rulings in grating. Now, how to eliminate those? Those ghost lines or ghost spectrum can be eliminated if interferometrically controlled ruling engines are used. Draw the grooving or draw the rulings in the grating, then they can be reduced. And secondly, if we implement holographic process, then the ghost lines or ghost spectrum or the errors in the grating can be eliminated. So interferometrically controlled ruling engine jodi use kora hoy to groove the grating, and also if holographic process are, then the ghost lines can be removed or eliminated. So there are different types of gratings are there: ruled grating, holographic grating and plane transmission grating. So in case of ruled grating, stray lights or the ghost lines that originates from the random errors and irregularities of the reflecting surfaces. And for holographic grating, so the holographic grating generates less number of ghost lines or ghost spectrum, because in optical process, in holographic process, the interference pattern produced in the grating are totally transferred to the photoresist that are used in holographic process. Next, I will discuss the resolving power and what is resolving power and the criterion that should be maintained for resolving power. Suppose we take two spectral lines that having wavelengths of lambda and lambda plus delta lambda, which are very close to each other, and they are coming from two different objects. দুটো ডিফারেন্ট অবজেক্ট থেকে ল্যামডা অ্যান্ড ল্যামডা প্লাস ডেল্টা ল্যামডা যারা হচ্ছে ভেরি ক্লোজ টু ইচ আদার, দুটো ওয়েভলেন্থের লাইট আসছে, then resolving power of a particular optical instrument is a measure of its ability to create individual image of the object instead of merged image. So the resolving power of an optical instrument is the ability to create individual images of those two objects instead of merged image. কোনো একটা optical instrument এর একটা resolving power বলতে বোঝায় ability of that optical instrument যেটা দুটো সেপারেট অবজেক্টসের ডিফারেন্ট ইমেজ ক্রিয়েট করতে পারবে ইনস্টেড অফ একটা সিঙ্গেল মার্জড ইমেজ। আমরা দ্যাট এবিলিটি অফ দ্যাট অপটিক্যাল ইনস্ট্রুমেন্ট উইল কল ইট ইটস রিজলভিং পাওয়ার। Then there is a criteria called Rayleigh criteria for resolving power, and that is followed by any optical instrument. Now what is Rayleigh criteria for resolving power? According to Rayleigh, two nearby images are said to be just resolved if they are separated by at least a certain minimum distance, so that position of diffraction central maxima of the first image coincides with the first diffraction minima of the second image in any order of diffraction and vice versa. So repeating again, according to Rayleigh criterion, two nearby images, দুটো কাছাকাছি যে images are said to be just resolved if they are separated by at a minimum distance. একটা minimum distance যদি সেই দুটো image থাকে যাতে position of the central diffraction max of first image and position of the minima of the diffraction for second image coincides for any order of diffraction and vice versa. তার মানে কি Rayleigh criterion অনুযায়ী বা Rayleigh criteria of resolving power অনুযায়ী দুটো নিয়ারলি ক্লোজলি স্পেসড অবজেক্ট তার থেকে যে দুটো ইমেজ তৈরি হচ্ছে সো দ্যাট প্রথম ইমেজের ডিফ্র্যাকশন সেন্ট্রাল ম্যাক্স will coincide with the diffraction mean of the second image for any order of diffraction. মানে যে কোনো অর্ডারের একটা পার্টিকুলার অর্ডারের জন্য প্রথম ইমেজের ডিফ্র্যাকশন ম্যাক্সটা মানে ডিফ্র্যাকশন ম্যাক্সিমাম যে পজিশন সেটা কোয়েনসাইড করবে সেকেন্ড ইমেজের ডিফ্র্যাকশন মিনিমার সাথে অ্যান্ড ভাইসি ভার্সা। তো এই ক্রাইটেরিয়াটা যদি মেনটেন হয় দেন দ্যাট ইজ কল্ড Rayleigh ক্রাইটেরিয়া ফর রিজলভিং পাওয়ার। তাহলে অ্যাকর্ডিং টু দ্য কন্ডিশন কী হবে, সাপোজ দিস ওয়ান ইজ দুটো অবজেক্টস আছে, দেয়ার আর টু অবজেক্টস, object 1 and object 2, their diffraction images are this one, this is for object 1 and this is for object 2. So 1 and 2 are two diffraction images of two objects which are closely spaced. Closely spaced. Then according to Rayleigh criteria, the diffraction max of the first image, that is this position, this is the diffraction max of the first image, that is max 1, that coincides with the diffraction mean of the second image. So this is the position of diffraction max of the first image and also the diffraction minimum of the second image. So they are coinciding. So they are coinciding and vice versa, means diffraction max of the second image coinciding with diffraction minima of the first image for any order, suppose for order n. So first image is having wavelength lambda, second image is lambda and delta lambda. So if this condition is satisfied, then it is called Rayleigh criteria for resolving power. So now we will find out the resolving power of a grating. So in case of grating, the resolving power refers to the power of distinguishing two nearby spectral lines and they are defined as resolving power R equals to lambda divided by delta lambda. So delta lambda means difference of the wavelength for two objects, difference between two closely spaced spectral lines. So in case of a grating, that resolving power would be lambda divided by delta lambda, which is also equals to m into n total, where m is the order of the spectrum and n total is the total number of lines present in the grating. That means টোটাল নাম্বার অফ যতগুলো লাইন্স আছে গ্রেটিংয়ে সেটাকে ডিনোট করে এন টোটাল দিয়ে, তাহলে রিজলভিং পাওয়ার অফ দ্যাট পার্টিকুলার গ্রেটিং উড বি আর ইকুয়ালস টু এম ইন্টু এন টোটাল, which is also equals to lambda by delta lambda, where delta lambda is the separation of two wavelengths which the grating can just resolve. So this delta lambda is separation between two wavelengths which the grating can just resolve. So this is the resolving power of grating. Secondly, we will discuss about resolving power of microscope. So for microscope, the resolving power is defined as the inverse of the distance between two objects that can be just resolved. So inverse of the distance between two objects which can be just resolved, that is called resolving power of microscope. In case of microscope, the distance between two objects let be delta d. Suppose distance between two objects be delta d. So delta d would be lambda divided by 2 into numerical aperture of the lens. Delta d would be, that is distance between two objects that can be just resolved. Delta d, that is equals to lambda divided by 2 into numerical aperture of the lens. Again, numerical aperture is lambda divided by 2 into numerical aperture value is n into sin theta, where n is the refractive index of the medium separating object and the aperture. So n sin theta is numerical aperture and where n is refractive index of the medium separating object and the aperture. This is the distance between two objects. Delta t equals to lambda divided by 2n sin theta. So resolving power would be inverse of that distance. So resolving power would be 1 divided by delta t, that will be equals to 2n sin theta by lambda. So this is the resolving power for microscope. Similarly, third case, that is resolving power of telescope. Here in case of telescope, we have to take the angular displacement. That means the angular separation between two objects, which is equals to 1.22 lambda divided by capital T, where capital T is diameter of the mirror. So delta theta separation, angular separation between two objects, that should be 1.22 wavelength used lambda divided by diameter of the mirror used, that is capital T. So resolving power would be 1 by angular separation, that is 1 by theta, that would be d divided by 1.22 lambda. So this is the resolving power for telescope. So we have discussed the resolving power of grating, resolving power of microscope and telescope. Next we will discuss a case which is describe the fringe pattern when the white light is incident on a grating. We will consider a case, or we will discuss a case where white light is incident upon the grating and what will be the effect of that after passing through the grating. So this came as a 3 marks question in the year 2023 for MAKAUT BTech physics question paper. The question was, describe the fringe pattern when white light is incident on a grating. Now, when a white light is passing through a grating, suppose this is the condition where white light is passing through a grating or diffraction grating. So there will be an interference pattern that will be produced and also the diffraction pattern. So together interference and diffraction pattern will be produced as a resultant spectrum on the screen, whose central will be white, because at the center position the path difference is 0. So at central point here the path difference is 0. So here it would be white spectrum, white light spectrum. But along the both sides of this white light spectrum, there will be spectrum of rainbow. That means both sides of the central white spectrum, there will be violet to red. That means Vibgyor spectrum would be formed for different wavelengths. As white light consists of 7 spectral lines, so for each spectral wavelength, there will be patterns or spectrum formed on the screen. Now, if you look at the formula for diffraction peak, d, that is for a particular wavelength lambda, d sin theta equals to m lambda. Now, for different lambda, that means white light consists of violet to red wavelength. So, for different lambdas, theta would be different for the particular order m. D is the corresponding points in the grating. So, d is constant. Only theta will change for different lambdas, as order number m and d constant. And for violet light, the wavelength is minima, and the red light, the wavelength is maxima. So for violet light, diffraction angle theta would be minima, and for red light, diffraction angle theta would be maxima. So on the both sides of the white spectrum on the screen, violet to red spectrum will be formed. So the diffraction grating will act like prism. In other words, polychromatic light source can be converted to monochromatic source by using that grating. This incident occurs when in the fringe pattern when white light is used or white light is incident on a grating. তাহলে ফাইনালি কি পাওয়া যাবে, স্ক্রিনের উপর সেন্ট্রাল পয়েন্টটা হবে হোয়াইট, আর হোয়াইট স্পেকট্রাম সেন্ট্রাল স্পেকট্রামের বোথ সাইডে পাওয়া যাবে ভায়োলেট থেকে রেড ভিবজিওর ফর্ম করবে both sides of the white spectrum, centrally white spectrum. 7টা কালারে প্রিজমের মতো হোয়াইট লাইটটা ভেঙে যাবে এবং both side of the central white spectrum তারা ফর্ম করবে. So this is the incident that will occur when white light passes through a grating. Now we will discuss about what are the difference between prism spectra and grating spectra. Now what we have learned that both produce polychromatic to monochromatic light. In case of prism spectra, only one spectrum is produced, whereas in case of grating spectra, a number of spectral of different orders are produced on each side of the central maxima. Second difference is prism spectra is produced due to dispersion, which is due to the different velocities of light wave having different wavelengths. So it is mainly due to the different velocities of different wavelengths. But in case of grating spectra, it is produced due to diffraction. The angle of diffraction is different for different wavelengths. So as a result of that, grating spectra of white light is produced. Thirdly, in case of prism spectra, red light is least deviated and maximum deviation is found for violet light. In case of grating spectra, the deviation is least for violet and maximum for red. Next difference is prism spectrum depends on the material of the prism, but grating spectra are independent of grating material. So these are the main differences between prism spectra and grating spectra. And from the diagram of both the prism spectra and grating spectra, you can visualize the difference. Next I will discuss diffraction in a crystalline material. Now what are crystalline solids? A solid is said to be crystal if it consists of regular periodic arrangement of either atoms, ions or molecules. Then that material can be said to be crystalline material. Now to discuss about crystalline material, some few topics that also should be discussed because they are very much important. Now number one is lattice. Now what are lattice? Lattice are regular periodic arrangement of points in space where each point has same environment as any other adjacent points. So this 3D arrangement of points in space is called lattice. So lattice is a mathematical concept. যেখানে হচ্ছে রেগুলার পিরিয়ডিক অ্যারেঞ্জমেন্ট অফ পয়েন্টস থাকে যাদের মধ্যে একটা পিরিয়ডিসিটি মেনটেন হয় এবং প্রত্যেকটা পয়েন্টের এনভায়রনমেন্ট হচ্ছে সিমিলার টু আদার অ্যাডজাসেন্ট পয়েন্টস। তাহলে এইরকম একটা পিরিয়ডিক অ্যারেঞ্জমেন্ট অফ পয়েন্টস ইন স্পেস ম্যাথমেটিক্যালি আমরা সেটাকে বলবো ল্যাটিস। নাও অ্যানাদার টার্ম ইজ দ্যাট which is called basis. Now if we put either atoms, molecules or ions on those lattice points, then those atoms, molecules or ions are called bases, and together the lattice and basis form crystal structure. তাহলে কি হলো? ল্যাটিস হলো রেগুলার পিরিয়ডিক অ্যারেঞ্জমেন্ট অফ পয়েন্টস ইন স্পেস যাদের প্রত্যেকটা এনভায়রনমেন্ট সেম, এবং ওই প্রত্যেকটা পয়েন্টে যদি আমরা কিছু আইদার অ্যাটমস, মলিকুলস আর আয়ন্সকে আমরা বসাই তাহলে ওই অ্যাটমস, মলিকুলস, আয়ন্সকে বলবো আমরা বেসিস, এবং ল্যাটিস এবং বেসিস দুটো একসাথে ফর্ম করে ক্রিস্টাল স্ট্রাকচার। তো ধরে নেওয়া যাক, suppose these points are lattice points. These are lattice points. They are arranged periodically and each of the points has same environment as any other point. This point or this point or this point. All points have same environment as any other adjacent points. Next, I will discuss about primitive basis vector or basis vector. Let R be the position vector of a lattice point with respect to an arbitrary point as origin, and similarly R prime be the position vector of another lattice point such that R prime is equals to R vector plus n1a plus n2b vector plus n3 into c vector, where n1, n2 and n3 are integers and a, b, c vectors are three coplanar vectors, and these ABC vectors are called fundamental or primitive translational vector or basis vectors. So, repeating again, we take R be the position vector of any particular lattice point. This is R vector with respect to origin O. Similarly, we take another point which has a position vector of R prime such that R prime becomes equals to, so R prime vector becomes equals to R vector plus a vector which is called T vector, where T vector is n1a vector plus n2b vector plus n3c vector, where a vector, b vectors and c vectors are three coplanar vectors যাদেরকে বলা হবে fundamental or primitive translational vector or basis vectors, and n1, n2, n3 are three integers. So 0 plus minus 1 plus minus 2 plus minus 3 and etc. তাহলে এই যে t ভেক্টরটা পাওয়া গেল, t vector which is equals to n1a vector plus n2b vector and n3c vector, this is called translational operator vector. তাহলে এই যে t vector which consists of 3 vectors small a, small b, small c vector, they are called fundamental or primitive translational vectors or basis vectors. তাহলে এগুলোকে আমরা বলবো basis vectors. Another term discuss করব that is called unit cell. Unit cell means that is the minimum amount of volume from which the entire crystal can be formed by translation of its own dimension. এটা একটা মিনিমাম অ্যামাউন্ট অফ ভলিউম যদি আমরা কনসিডার করি, একটা স্ট্রাকচার কনসিডার করি উইচ হ্যাজ এ মিনিমাম অ্যামাউন্ট অফ ভলিউম, অ্যান্ড সেই মিনিমাম অ্যামাউন্ট অফ ভলিউম থেকে পুরো ক্রিস্টাল স্ট্রাকচারটাকে আমরা ফর্ম করতে পারবো বাই ট্রান্সলেশন অফ দ্য ডাইমেনশনস অফ দ্যাট মিনিমাম অ্যামাউন্ট অফ ভলিউম। তাহলে এইরকম মিনিমাম অ্যামাউন্ট অফ ভলিউমস এক একটা যে স্ট্রাকচার দ্যাট আর কল্ড ইউনিট সেল। And 3 sides of that unit cell can be represented by these 3 fundamental primitive translational vectors, A vector, B vector and C vector, which are coplanar vectors, or which are also called as primitive translational vectors or basis vectors. Now, suppose this is the lattice points where we take this as origin. Now a position vector of this point is with respect to the origin is B r vector, and position vector of B r prime vector, such that r prime vector would be equals to r vector plus translational operator t vector, which is equals to n1 a prime a vector plus n2 b vector plus n3 c vector. কি হলো, এই this vector is translational operation or translational vector t vector, where r prime equals to r vector plus that translational operator. So here a vector, b vector and c vector are called primitive vector or basis vector. Next I will discuss about what are lattice planes. In previous slide we have discussed about what are lattice points. So lattice points or simply lattice of a crystal may be considered as composed of infinite sets of parallel equispaced planes. তাহলে এই যে প্লেনসগুলো, the distance or perpendicular distance between those planes are called interplanar spacing. কি বোঝা যাচ্ছে যে space lattice বা lattice যে point, those lattice points can be considered as a set of or composed as a set of infinite parallel planes which are equidistant to each other, and those planes are called lattice planes. Those planes are called lattice planes, and the distance between two such planes are called interplanar spacing. Now suppose these points are lattice points, this one etc., all are lattice points. So we can consider those points in 3 dimension as set of parallel planes. Those set of planes can be this one, either this one or this one, or either this one, this and this one. So we can imagine that in 3 dimension all those lattice points are such that they are composed of an infinite set of equally spaced parallel planes. তাহলে এই যে দুটো planes, suppose for এই lattice planes গুলোর জন্য এই দুটো planes এর in between distance that is called interplanar spacing, which is denoted by d. So this is interplanar spacing. Similarly for here this distance is d, interplanar spacing. So এই রকম planes গুলোকে বলা হবে lattice planes. Now what are Miller index or Miller indices? এই যে each set of lattice planes যেগুলো আমরা কনসিডার করলাম, so those each set of lattice planes has a particular orientation about the crystallographic axis. So in crystal arrangement is in 3 dimensional, so we can consider 3 crystallographic axes. So those set of lattice planes has a particular orientation about those crystallographic axes. Now Miller indices describes a particular set of lattice planes. So what are Miller indices? Miller indices describes a set of particular planes which has a definite orientation with respect to crystallographic axis, and those planes are denoted by the Miller index. And how is it done? Suppose one such plane is LMN. This plane is one such plane. So this is one plane. So this plane will intercept the three crystallographic axes OX, OY and OZ, and let be the intercepts lengths be PA for OX, QB for OY and RC for OZ. কি হলো, একটা প্লেন সাপোজ কনসিডার করলাম একটা প্লেন এলএমএন প্লেন, যেটা তিনটে ক্রিস্টালোগ্রাফিক অ্যাক্সিসকে যারা যথাক্রমে হচ্ছে ওএক্স ওয়াই ও জেড কে ইন্টারসেপ্ট করছে লেন্থ হিসাবে কত পিএ, যেখানে পি হচ্ছে একটা ইন্টিজার একটা নাম্বার, পি মাল্টিপ্লাইড বাই আর পি হচ্ছে একটা নাম্বার, আর এ হলো ম্যাগনিটিউড অফ দ্য primitive translational vector or primitive basis vector a vector, and similarly intercept করছে OY axis কে LMN plane QB, যেখানে Q হচ্ছে একটা নাম্বার এবং B হলো magnitude of vector basis vector B vector. Similarly OZ axis কে RC length এ intercept করছে. তাহলে then H is to K is to L, we can write it as 1 by P is to 1 by Q is to 1 by R, where P, Q, R are three numbers such that ratio 1 by P is to 1 by Q is to 1 by R should be such that they don't have any other common factor rather than 1. মানে এই 1 H K L, H is to K is to L এই রেশিওটা এরকম হবে যাতে 1 by P is to 1 by Q is to 1 by R এর কমন ফ্যাক্টর 1 ছাড়া আর কোনো যেন কমন ফ্যাক্টর না থাকে. দেন দ্য মিলার ইন্ডেক্স ইজ ডিনোটেড অ্যাজ ইন ফার্স্ট ব্র্যাকেট এইচ কে এল. তাহলে কি হলো ব্যাপারটা, যে এইচ ইজ টু কে ইজ টু এল উড বি সাচ দ্যাট ইজ বিকামস ইকুয়ালস টু 1 by P is to 1 by Q is to 1 by R, where intercept of the crystallographic axis OX is PA, where intercepts of the crystallographic OX is OY would be QB, and similarly OZ would be RC for that particular plane. Then H is to K is to L, the Miller index can be written as equals to 1 by P is to 1 by Q is to 1 by R, such that these ratios doesn't have a common factor other than 1. Then we can write HKL value that we can write in first bracket, and that is represented as Miller index of that plane LMN. So this is how Miller index can be found. তাহলে কি হলো, পার্টিকুলার একটা সেট অফ প্লেনসকে ডিনোট করবে এই মিলার ইন্ডেক্স. সো ইম্পর্টেন্স অফ দ্য মিলার ইন্ডেক্স কি, দ্যাট মিলার ইন্ডেক্স ডিসক্রাইবস নট এ সিঙ্গেল প্লেন, এ সেট অফ প্লেনস হুইচ আর প্যারালাল অ্যান্ড ইকুইডিস্ট্যান্ট টু ইচ আদার. দেন দেয়ার ইজ এ রিলেশন বিটুইন ইন্টারপ্ল্যানার স্পেসিং অ্যান্ড মিলার ইন্ডেক্স. যে ডিফারেন্ট প্লেন্সকে আমরা কনসিডার করলাম, ডিফারেন্ট ক্রিস্টালোগ্রাফিক প্লেন্স অর ল্যাটিস প্লেন্স, তাদের যে ইন্টারপ্ল্যানার স্পেসিং অর ডিস্টেন্স বিটুইন টু সাচ প্যারালাল ইকুইডিস্টেন্স প্লেন্স দ্যাট ইজ ডিনোটেড অ্যাজ ডি, তার সাথে মিলার ইন্ডেক্সের যে রিলেশন, অ্যান্ড এই মিলার ইন্ডেক্সের সাথে ডি এর যে রিলেশন, the relation between D and HKL is given as this one, D equals to 1 by root under H square by A square plus K square by B square plus L square by C square, where A, B, C are the dimensions of unit cell and HKL is the Miller index. A derivation that is not in your syllabus, so it has not been discussed here. And for simple cubic case, the dimensions of the unit cell are equals, that means A equals to B equals to C. So for simple cubic crystal, the D versus D and HKL relation would be D equals to A divided by root under H square plus K square plus L square. So this is the relation between interplanar spacing and Miller index. Now each topic I am discussing here is according to the MAKAUT BTech physics syllabus, paper code PH101 or 201. সো এই পেপার কোডের বা এই সিলেবাসের যে যতটুকু আছে ডিফ্র্যাকশন পার্টের মধ্যে, ডিফ্র্যাকশন ফ্রম ক্রিস্টালাইন ম্যাটেরিয়াল, ততটুকুই দ্যাট হ্যাজ বিন ডিসকাসড হিয়ার. এর বেশি এর ডিটেলে ডিসকাস করা নেই, যতটুকু সিলেবাসে দরকার ততটুকুই এখানে আমি ডিসকাস করি. নেক্সট topic I will discuss, that is called Bragg's law for X-ray diffraction. Let a beam of monochromatic X-ray of wavelength lambda be incident on such lattice planes within a crystal, and the glancing angle of the incidence suppose be theta. Glancing angle means if this is the plane and this one is the X-ray and it is the diffracted ray, then this angle is called glancing angle. Now suppose we are using X-ray having a wavelength of lambda and that is incident, and we are projecting it towards a crystalline material, and those X-rays are incident at a glancing angle theta on a set of parallel such lattice planes which are equidistant to each other. And suppose D be the interplanar spacing, that means in between these two planes, suppose this distance is D, so the interplanar spacing is D. So suppose one ray is incident upon here, and after diffraction from this lattice point it is going to this direction, and second X-ray is incident and after diffraction it is going to this direction. So distance between these two planes be interplanar spacing. So we have to calculate the path difference travelled by this ray 1 and ray 2. And what would be the path difference? Path difference would be, suppose we draw a perpendicular from this point to this and this point to this. These are two perpendiculars. So this is the glancing angle theta. So similarly these two would be the glancing angles, which will be also theta. So here the optical path difference between this ray 1 and ray 2 would be only this part and this part. So if the interplanar spacing in this is D, then this length and this length would be d sin theta plus d sin theta. Extra path travelled by the ray 2 would be d sin theta plus d sin theta, means this distance plus this distance, that is total is 2d sin of theta. If the optical path difference 2d sin theta is equals to n lambda, so this is the Bragg's law for X-ray diffraction, where n equals to 1, 2, 3 integer numbers. From Bragg's law or from crystalline, from X-ray diffraction from crystalline material, another question that is very much important, which is why X-ray are most useful for crystal analysis. Structure of crystal, why X-rays are used? In other words, why visible light is not Bragg reflected? The দুটো question same, এটা হলো X-ray কেন ইউজ করা হয় for crystal analysis or Bragg reflection or Bragg diffraction. Secondly, visible light কেন ইউজ করা হয় না বা visible light কেন Bragg reflected হয় না. Now from Bragg's law we get 2d sin theta equals to n lambda, which is the Bragg's law of diffraction. From here we can get sin theta value is maximum 1. So sin theta would be less than 1. Sin theta less than 1 means from here we get sin theta value means n lambda by d, m lambda by 2d, which is less than 1, or for a particular order, fixed order n, we get lambda divided by 2d less than equals to 1 or lambda less than equals to 2d. That means the wavelength used for diffraction should be less than the order of interplanar spacing d. So the wavelength and the interplanar spacing should be of same order. So the wavelength used and the interplanar spacing should be of the same order or the same dimension. So for X-ray we know wavelength dimension is around angstrom, and similarly for interplanar spacing d of any crystal is also of the order of angstrom. So both matches. So for that reason X-rays can be Bragg reflected, or X-ray are mostly useful for crystalline analysis. For visible light, which is around 400 to 600 nanometer. So wavelength of visible light is around 400 to 600 nanometer, which is very much greater than interplanar order of the interplanar spacing, which has a order of angstrom. So visible light cannot be used, or visible light cannot be Bragg reflected. So only X-ray should be used or should be Bragg reflected. This is the answer. So this is the last video for the diffraction under optics part. of MAKAUT BTech Physics syllabus. So all the topics I have discussed according to the syllabus. যতটুকু সিলেবাসের মধ্যে আছে ততটুকুনি আমরা এই ভিডিওর মাধ্যমে আমরা সেটাকে প্রেজেন্ট করার চেষ্টা করেছি। So see you in the next video with a new chapter of MAKAUT BTech Physics syllabus. Till then, bye.